All right, welcome back to part 2. We just got done pinging between nodes and we watched the simulation, but we really want to understand what just happened there. So I'm going to move everybody over a little bit here. Let's try that again. There we go. All right, we're going to do our simulation, and I'm going to take that same ping. Now we won't have the ARP messages this time, but we will have the ICMP, which is really what we want to well, actually, let's go ahead and do it. We'll do it step by step because this is really informative. Let me make sure that my ARP table here is clear. So I'm going to use a different node. You know what? We use the same node. All right, so what I'm worried about here is I want to see the ARPs. And so the reason I won't see the ARPs is because there's something in the ARP table here. And Packet Tracer is not really handy at letting my nodes clear my ARP table, so I'm just going to disconnect this line here and then reconnect it to port 7. So that's a handy way of doing this. And so now if I look at my ARP table with an ARP-A, there's nobody in there. So that'll force the generation of ARPs again. And so we are just going to watch this as it goes, and we'll wait for the port to go forwarding. That's 30 seconds. A little more detail on spanning tree. Spanning tree uses a lot of states to figure out what's going on. So what's happening now is when you bring a port up, the first thing it does is listens, and it's trying to understand whether or not there are other switches out there because it's looking for loops. And then it goes into learning. The learning state, and each one of those states is 15 seconds, so 15 plus 15, 30 seconds. That's why it takes almost exactly 30 seconds for this to go forwarding. And then once it does that, spanning tree is happy and we'll forward the ports. Oh, I forgot we're not in real time here. Shoot. So all that time I just spent talking was wasted, but why not? We'll show you more spanning tree stuff. All right. So here is the some of the data that spanning tree uses. Each bridge gets an ID, which is a combination of the priority and a switch, and they communicate this back and forth. And you can see here that this is the status of my ports, and spanning tree actually is aware of the different VLANs. So there's the a couple of different states. There's learning and there's forwarding. All right. So now it's gone green, so everybody will be forwarding, right? These two ports are forwarding. These two ports are forwarding. And these guys are forwarding too. All right, so we're ready to go. I'm going to go back to my simulation so we can start freezing time. And I'm going to go ahead and ping. So on this node, which is on the 12 net, we're going to go to the 11 net. So we're going to have a lot going on here. And let's see. I want to make sure that everybody's, I guess we're okay. I was going to clear the router ARP tables too, but I'm not going to worry about it. All right. So here we go. So we can see the ICMP and the ARP queued up. The ICMP, when we ping, we're generating ICMP echo requests. And so the ICMP is what we want to send. But in order to send that, we need to learn the MAC address of the default gateway. So we'll put this down here, and here it goes. So now it goes down to this particular switch, and it came in on VLAN 12. So the switch says, I've got to send this out VLAN 12 only and any trunk port. So it goes across the trunk as well. Now there's nobody else in VLAN 12 over here. Now, what just happened? If we take a look at the ARP message that left PC7, right? It looks normal. It's coded as an ARP type. It's got a broadcast destination MAC address. This is where it came from. This is the IP address, and this is the MAC address that I need for that IP address. But what happened when it went across the trunk line? Well, we find out that there was a fundamental change to this frame. Right here we've got these extra fields. And these extra fields really are about this guy right here and this guy right here. So we're now trunking. So this is not standard Ethernet. The frame looks different going across the trunk line than it did coming from the PC. And we did what's called 802.1q tagging, IEEE 802.1q. And so it changes the protocol ID from 0806 to 8100. Now, the chocolatey, crunchy goodness here is mostly about the VLAN ID. Now, there are other things there. You can take a look at the other videos about an in-depth description of this, but this is really about the priority, the canonical format, but really this is what we care about, the last 12 bits that's allocated for the VLAN ID. And we can see it's 0C, and 0C, if you convert that to base 10, is VLAN 12. So that's why the switch knows when it gets over here to switch 0, that's how the switch knows how to format it. So I was counting in hexadecimal there, so 9 is 9, A is 10, 11, 12 for C. When this traffic leaves switch 2, it is tagged with VLAN 12. It goes all the way across here, and the switch on the left, switch 0, says, oh, you are tagged for VLAN 12. Let me send this broadcast out VLAN 12. So let's see what that looks like. Look at that. It goes to all of these nodes that are part of VLAN 12, including the router. The router gets it and says, oh, you are looking for my MAC address. Let me answer. Nobody else does. And it goes back across the trunk. Well, what does it look like when it goes back across the trunk? Well, it's tagged for VLAN 12 again. So that router interface is on VLAN 12. It's answering with the ARP response on VLAN 12. And then we send it across to the other switch. This switch gets it, says, oh, you're tagged for VLAN 12. Let me send it to VLAN 12. And actually, by this point, the switches are starting to learn the MAC addresses. So now, when we take a look at our MAC address table, now we realize the importance of that VLAN ID. When we look at the MAC address table, we can see, oh, everybody's not in VLAN 1 anymore. We're learning that MAC addresses are not only attached to a particular port, but they're also attached to a particular VLAN. And we start to realize that, or maybe we remember, that multiple MAC addresses can be associated with a single port. Okay, so our forwarding is fundamentally updated. So now this goes back across, and now we're at the ICMP messages. So they go back across, again, tagged with VLAN 12. Okay? So it goes up to the router handles it, and it goes down to the proper node. Okay. Well, let's do one more. What happens when PC5, go back to real time here. So what happens when PC5 and PC7 want to communicate? Remember that their default gateways are way over here. So let's find out. So PC5 is now going, well, maybe we'll do it, since we're used to it, we'll do this same PC. So now we're going to go just down to same network, but 11.5. So instead of going over here, we're going to go right here. And you would think they're connected to the same switch. This will work fabulously. I am just going to go send it right over there. Let's see what happens. So now at this point, we won't see much of the ARPing anymore, or as much. This may have timed out down here, but because we've already learned the MAC addresses of the router. So off we go. So it goes down to the switch. Switch says, oh, you're on VLAN 12. Let me send this out VLAN 12 and any trunk port. Goes across the trunk because, of course, this PC needs to talk to its default gateway. Because, of course, this PC needs to talk to its default gateway to get to somebody on a different network. So it goes across the trunk, tagged as VLAN 12. Goes up to the router. The router says, let me check my router routing table. Right? It says, oh, I know where that destination network is. let me send it out. And the router has already learned the MAC address of 11.5, so he sends it back across. Now, this switch, why did this go everywhere? This switch at this point had forgotten the MAC address of this node here. The router remembered it, because routers are really aggressive about keeping their ARP tables populated, but the switch forgot it. So this is not a broadcast frame, right? Not a broadcast frame. These, instead, what the switch did was he forgot. So the switch is trying to find PC5. And so this is flooding, which is different than broadcast forwarding. The switch is now just trying to find this MAC address because it wasn't in. We take a look here, and we take a look at our show MAC address table, right? The MAC address that it was looking for was at this point not in the source address table. So let's take a quick look, see if we can find it. Well, how do we figure that out? Well, if we look at the MAC address in the message, right, the destination is right here, and it ends in 33E7. If we look in the source address table, 33E7 does not appear in my source address table. So the switch says, I don't know where to send this. So when we flood, it's the same thing. Every port except the one that it came in on and any trunk. So that's why it goes across the trunk. The router, oops. The router knows. So there's 33E7 right there. So as I said, routers are pretty aggressive about populating their ARP tables and maintaining entries. So we just keep this going. Oops, wait, I forgot. We're on a different network now. So different VLAN. So when this goes across the router, look at the tag now. VLAN 11. So when it comes to switch 2 gets it, says, oh, I see you're tagged for VLAN 11. Now I can send this to the proper VLAN, and it goes down to the destination. So when you think about it, it was crazy, right? When I'm going to talk between these two PCs, it goes all the way across to the router, back up, back down, and then back across. So that was the ICMP echo reply. So here it goes again. Here's the request. Up to my default gateway, down, across, tagged for VLAN 11, and then to the destination. So that is the way that tagging in trunks work. And what this means is that not only do I not need a router over here, I can connect lots and lots of distant networks or distant nodes to their default gateways across trunk lines. So we could even get crazier, right? So I just realized that I've got a dotted line here and a straight through here, and so this indicates a crossover cable. So I'm going to go ahead and be, I will leave it. I'll just make a comment on this. So older switches are not often smart enough to negotiate the crossover. Same thing with hubs. And when you connect routers together, those interfaces a lot of times on older gear could not auto-negotiate the connection. So we use crossover cables. The reason we use crossover cables is so we could cross transmit to receive lines. But most modern communication gear is smart enough to figure out what the pins are supposed to be, almost independent of what kind of cable you used. But if you were going to be really, really clear that you understood what was going on, you would put a crossover cable between your switches, and between PCs that are connected to each other, between routers that are connected to each other. Well, there we have it. Okay, let's add to our topology a little bit. So I'm going to make this guy, this host, we'll put, I don't know, we'll mix things up a little bit on the bottom. We'll say that this is 172.16.12, and we'll make this .6. So if it's going to be 12.6, it's got to go to 12.254. Now, if you are trying to remember all of the things that need to be done, you pause the video right now and see if you can come up with all of the stuff that needs to be done to bring this poor lonesome node into the network so that it can communicate with everybody else. So pause the video if you're going to try and figure it out yourself, or write down what has to be done. On your mark, get set, go. Here I go. All right, so first up, I've got to connect this host to the correct VLAN. So what I'm going to do is config T, we'll say, here's our host name. This just helps me keep track of all the different consoles I have open. And we're going to say interface F0/6 switch port access VLAN 12. And what port are these ports? This is 24 and 24. Okay. So that means that I need to make 24 and 24 trunk lines. So int F0/24 switch port mode trunk. Now I will show you one other thing that I just remembered. If I do a show VLAN now, I will see that port 24 on switch 3, right? We're on switch 3. Port 24 does not show up in VLAN 1 anymore, because the minute you make a trunk line, you're not in a VLAN anymore. And in fact, you should not. Do not add a VLAN tag to a trunk line. Very, very bad. Okay, so let's go over to switch 2. Oh no, we've got that inconsistent type. Look at this. We've got BPDU stuff here happening. There's that 802.1q, right? So switch 3 wants to be a trunk, and switch 2 is sort of getting in the way of that. Now, a lot of switches, as I said, will have a lot of auto negotiation capability. Dynamic trunking protocol is one way we do that, but I'm going to go ahead and say, listen, F0/24, you need to be a trunk, buddy. Switch port mode trunk. And that should make everybody pretty happy. All right, so now we're labeling here. We've got a trunk, and that means that it's IEEE 802.1q in Cisco speak. That's actually .1q like this. And this one is also a trunk doing IEEE 802.1q. Now, what IEEE 802.1q does is it specifies, among other things, all of that formatting that we saw when we were tagging frames. So all of that is in IEEE 802.1q. 802.1q also encompasses all of the stuff that was previously in 802.1d. So spanning tree is there, the behavior of layer 2 switches is there, all of that, store and forward. All right, so let's see if we can get around our topology now. We'll go all the way across. Yeah, let's go ahead and trace this while we go. And we will go to a different, let's go to a different network. So we'll try 172.16.11.1. Go all the way over there. So that's this PC6 all the way over here. And we'll watch the tagging as we go. Alright, so again, we're ARPing. Who are we ARPing for? Well, this host processed its host routing table, got all the way to the all through the entries, and said, oh, I can't get there. By the way, if you're playing the home game, I'll show you a quick example of a routing table. When I say I'm processing the host routing table, I'm processing this thing right here. Now, this is my host PC, so it's not, doesn't have anything to do with our topology, but this is what you're doing. You're trying to find the answer to your packet. So what route do I use to get to the destination? When this host does that, it finds out that it doesn't have a path to the destination, and so it needs the default gateway help. So this ARP request is going to be, I'm looking for the MAC address that goes with my default gateway. And what I'm going to do after that is I'm going to populate my ARP table. We'll see that here in a second too, I guess. All right. So it goes up. Remember that this is VLAN 12 over here, so it's tagged with VLAN 12. All right, so we're a trunk here. We go across. Oh, look, it went up to VLAN 12. Why? Because switch 2 says, well, my rule is I've got to take broadcast traffic and send it out every VLAN that matches plus any trunk. So we've got VLAN 12 right here. So it goes up to this node. And of course, it gets blasted out on VLAN 12 over here. Comes back down. It'll be tagged for VLAN 12 going all the way back across, but now everybody knows. Everybody's learned now where 12.6 is MAC address is. So if I take a quick look at that and I say, well, what is the MAC address I'm looking for? D741. Well, switch 3 knows that D741 is attached to port 6. From the perspective of switch 2, though, D741 is connected to port 24, and that makes sense. This is port 24 here going over, so from the perspective of switch 2, it lives on this port right here. From the perspective of switch 0, D741 is connected to port 23, which is this port right here. So that makes sense. From switch 0, it just says everybody's that way. Okay, so we'll keep going. Now this ICMP is destined for 11.1. Again, tagged with 12. It'll be tagged with 12 over on this side too because, well, heck, we're still on VLAN 12. It won't wind up on VLAN 11 until it gets to this switch over here. But first it's got to go up to the router. Router makes a routing decision, says, I know where that network is, and I know where that MAC address is. Oh no, the switch forgot it. So it sends it out all ports, except the one that it came in on VLAN 11. And it also sent it across the trunk. Anybody know where this MAC address is? Because I don't. There it is, tagged with VLAN 12, right? We're looking for this. It's the ICMP message. The switch just doesn't know where to send it. Well, does switch 2 know where to send it? Switch 2 doesn't know either. Switch 2 has never seen that MAC address. So it sends it out VLAN 11 and this trunk over here. Switch 3 just says, yeah, I'm done. I don't need it. Okay, so we've got this answer coming back. So we'll just follow this through again. So now we should have everybody resolved. Everybody should know where the MAC address is, so now it should be a straight shot to the router and then back down. So up to my switch, the switch now knows it lives over there. Switch 2 knows where it lives, so it sends it over there. Up to the router. I know where this network is. I know where the MAC address is. I built the frame. Switch says, I know where that MAC address is now, and answers back. And there we have it. Well, let's do one more thing here. We'll go to real time. This is terribly wasteful as far as the topology goes because I've got this router way over here, and as my network grows, these hosts, if I wanted to communicate between another host on this network or on this switch, if I put another one up here and I say that this node was going to be, I'm not going to connect it because we're going to do something else later on, but if I wanted to make this guy 12.8 or 11.8, right? That means that I'd need these VLANs here, and for these two nodes to communicate, they'd have to go all the way over here to this router and then all the way back. All right, so maybe there's an easier way to do that. Plus, I've got this router up here, and maybe I don't need the router because there are switches that can be a little bit smarter than that. Now I'm looking at my time here, and I'm getting pretty long again. So I think we're going to go ahead and do a part 3 to do this last configuration. Okay, so I'm going to pause right here, and then we'll come right back in, and we will pick up adding a multi-layer switch and maybe making our topology a little bit more efficient and do some pruning.